Hello, bedtime thinkers, and welcome to the Bedtime Discoveries. I'm so glad you're here with me tonight. Take a slow breath, let the day gently fade away, and allow your mind to drift into the quiet comfort of science stories made for sleep. Tonight we will explore how life manages to survive in the most extreme places on Earth, places that seem too hot, too cold, too deep, or too harsh for anything to live, and yet life always finds a way. Before we begin, I'd love to know where in the world you're listening from tonight. If you like, you can share your location and the time where you are down in the comments. It's always wonderful to see this little community connecting across so many places on our planet. And if you find these bedtime explorations relaxing, please remember to gently tap the like button and softly subscribe to the Bedtime Discoveries so you can drift off with us again night after night. When we use the word extreme in everyday life, we often mean something intense, something far beyond what is ordinary. But in the world of science, the term carries a very careful meaning. An extreme environment is a place on Earth where conditions make survival nearly impossible, at least for the kind of life we are most familiar with. For humans, and for many animals and plants, survival depends on a delicate balance. We need a range of temperatures, not too hot and not too cold. We need water in liquid form, not locked away in ice, and not boiled away as steam. We need air with just the right amount of oxygen, and we need food, shelter, and some stability in our surroundings. When these things are missing, or when conditions shift too far away from that balance, we call extreme. Imagine a desert, where the air is so dry that water disappears almost instantly from the surface of your skin, or the bottom of the ocean, where the pressure is so heavy that it could crush a submarine made of steel, or a frozen glacier, where temperatures never rise above freezing, even the height of summer. To us, these places seem hostile, unwelcoming, perhaps even lifeless, and yet life has found ways to exist in them. These survivors, known as extremophiles, push the limits of what biology can achieve. They remind us that the definition of home in nature is far broader than we once believed. Scientists often study these places not just out of curiosity, but to understand the boundaries of life itself. Where does life stop working? And where does it continue against all odds? Every time we think we discovered the limits, nature shows us a new surprise. Life stretches a little further and reveals that survival is more flexible than we imagined. In this gentle exploration tonight, we will walk slowly through some of Earth's most challenging environments: the boiling heat of volcanic pools, the freezing grip of ice and snow, the crushing pressure of the deep ocean, the thin air of high mountains, the dry emptiness of deserts, the acidic waters of strange lakes, the invisible dangers of radiation, and even the silence of space-like conditions. Before we reach those details, we must first understand that extreme is always a matter of perspective. What feels impossible to us might be perfectly ordinary for a different form of life. To appreciate what extreme means, let's think for a moment about the human body. We are delicate creatures, more fragile than we sometimes realize. Our body temperature must remain close to 37 degrees Celsius, or 98.6 degrees Fahrenheit. If it falls just a few degrees too low, or rises a few degrees too high, our organs begin to fail. We cannot drink salt water. We cannot breathe air that lacks oxygen. We cannot withstand high doses of radiation, and we can survive without water for only a handful of days. Because of these limits, When we step outside of comfortable zones, we call them extreme. A desert, for example, may feel unbearable to us, but to a cactus, it is not only survivable, but actually perfect. A cactus has adapted to store water in its flesh, to close its pores tightly, and to wait patiently through long stretches of heat. In the frozen Arctic, where the air bites at our skin, some species of fish swim calmly, with antifreeze proteins in their blood. What kills us is simply ordinary life for them. This perspective reminds us that extreme is not absolute. It is relative to the design of the organism facing it. What is unthinkable for humans may be gentle and comfortable for microbes, plants, or other creatures. This is one of the reasons why scientists love to study extremophiles. They reveal the hidden flexibility of life. They show us that biology is not fragile, but remarkably creative. Where we see a wall, life finds a doorway. And so, when we begin to explore these unique environments, we must do so with an open mind. What seems deadly to us might be an invitation for another form of life to flourish. There's also another way to think of extremes, not just in physical terms of temperature, pressure, or chemistry, but in the way life bends and adapts to conditions that appear at the very edge of possibility. Take the concept of energy. Most life that we know depends on sunlight. Plants capture it. Animals eat plants, and energy flows through the chain of life. But in extreme environments, sunlight may not be available at all. Instead, organisms learn to feed on chemicals or to recycle tiny amount of energy in ways we could hardly imagine. In some places, extremes are not only physical, but temporal. That is, they last for immense stretches of time. In the deep earth, microbes have been found that live so slowly, their life cycles span thousands of years. To us, such slowness seems extreme. Yet to them, it is simply the pace of survival. There are also extremes of space. Tiny pockets of water, trapped inside rocks, deep below the surface, or microscopic droplets in clouds, high above the earth. Both of these can serve as habitats, hidden worlds for small but determined forms of life. When scientists define extreme environments, they often create categories: high heat, low temperature, high pressure, high radiation, no oxygen, high salinity, extreme acidity, extreme alkalinity. Each category pushes the known limits, and within each one, we discover forms of life that thrive. The fascinating part is this: as we expand our knowledge of Earth's extremes, we also expand our imagination of life elsewhere. If microbes can survive boiling pools or frozen deserts, then perhaps life beyond our planet may not require the gentle Earth-like conditions we once assumed. Perhaps Mars, Europa, or other distant worlds hold surprises, waiting quietly beneath their surfaces. So when we speak of extremes, we are not only describing the edge cases of life on Earth, we are also opening a window to the wider possibilities of existence. Extremes are not barriers, but invitations, and life, again and again, accepts the challenge. When we think of heat, most of us imagine summer days, sunlight pouring down on the skin, the shimmer of air above a hot road. But the places we are about to visit go far beyond the warmth of summer. They are realms where water boils, where rocks themselves glow with fire, and where the air trembles with rising steam. To us, such heat feels unbearable. Our bodies overheat quickly, our proteins unravel, our cells collapse. But deep beneath the surface of the earth, and even in open pools on the surface, life has learned to endure the searing world. Scientists call these survivors thermophiles, a word that means heat-loving. They are mostly microbes, invisible to the naked eye, and yet they shape entire ecosystems, feeding other forms of life, producing strange colors in hot springs, and rewriting our understanding of survival. One of the most famous places where thermophiles thrive is Yellowstone National Park in the United States. If you've ever seen photographs of its hot springs, you may remember the brilliant rings of color. The center of the pool is a bright blue, surrounded by bands of yellow, orange, and deep red. Each band is created by communities of heat-loving microbes. Each color marks a slightly different temperature zone, where a unique group of organisms makes its home. At the very center, the water can be near boiling, too hot for most life, but as the temperature drops outward, bands of thermophiles bloom, each adapted to its own narrow range. Together, they paint the earth in colors that are not only beautiful, but alive. These heat-loving microbes are more than curiosities. They have enzymes, tiny molecular machines that function even at temperatures close to 100 degrees Celsius, where most enzymes would fall apart. Theirs continue working smoothly. This discovery has been so valuable that scientists use some of these enzymes in modern medicine and technology. The very process of copying DNA in laboratories around the world relies on an enzyme from a Yellowstone thermophile. So already we see that life in extreme heat not only survives, but contributes to the tools of science itself. In the glowing pools and steaming vents, life has written new chapters of resilience. Now, let us descend far below the surface of the sea, down into the midnight blackness of the ocean floor. Here, in a place with no sunlight at all, heat rises from cracks in the earth. These cracks are called hydrothermal vents. At these vents, seawater seeps into the crust of the earth, heats up in the depths, and then bursts back into the ocean. The water that gushes out can reach 400 degrees Celsius. That is far hotter than boiling. And yet, around these vents, life flourishes. Imagine for a moment, standing at the base of the ocean, in total darkness. All around you, strange chimneys of black smoke are rising. They are not made of smoke, but of minerals carried up by the superheated water. And clustered near these chimneys are entire communities of life. There are giant tube worms, as long as a person, with bright red plumes waving gently. There are ghostly fish, crabs, clams, and shrimp, and living beneath them all, supporting the food web, are thermophilic microbes. These microbes do something remarkable. They do not depend on sunlight. Instead, they use the chemicals in the vent water, hydrogen sulfide, iron, and other minerals, as their source of energy. This process is called chemosynthesis. It is a way of making food, not from light, but from chemical reactions in this dark and hot world. Entire ecosystems exist completely independent of the sun. This discovery amazed scientists when it was first made in the late 1970s. It showed that life does not need sunlight to survive. It needs only energy in whatever form the earth provides. And so, the ocean's fire, once thought deadly, becomes a cradle of life. An environment we thought of as extreme turns out to be rich and even nurturing in its own extraordinary way. Heat is a powerful force. It can destroy, but it can also sustain. The story of life in scorching places teaches us that survival is about adaptation, not avoidance. Think for a moment about the enzymes in our own bodies. They are comfortable only in a narrow range. But thermophiles have reshaped their enzymes. Their proteins are locked together more tightly, resisting the unraveling that heat usually causes. Their membranes are thicker, their chemistry more resilient. This means that life does not stop at the boundaries we assume. It bends, reshapes, and reinvents itself to fit even the hottest worlds. And there is a larger lesson here. When we look beyond Earth, at planets and moons where temperatures soar, we might be tempted to say, nothing could live there. But the thermophiles remind us that life has many ways of saying yes where we imagine no. In fact, NASA and other space agencies study these heat-loving microbes carefully. They are models for what life might look like on other worlds. If volcanic activity exists beneath the ice of Europa or in the crust of Mars, then perhaps microbes like these could endure. And closer to home, their adaptations are already helping us. From DNA technology to industrial processes, we borrow from the lessons of the heat. What was once thought impossible now enriches both science and daily life. So when we think of heat as an enemy, it is worth remembering that for countless tiny organisms, it is not a danger, but a home. And where heat rises, life often rises with it. Cold is silence. It settles over landscapes like a soft, heavy blanket, slowing every movement, freezing every drop of water, and pressing time into stillness. For humans, extreme cold is unforgiving. Our skin stiffens, our breath turns to frost, and our cells begin to break apart when the water inside them freezes. And yet, Earth holds vast regions of such cold, and life, astonishingly, has made its home there. The polar regions, the high mountain glaciers, the icy depths of oceans, even frozen deserts where snow rarely falls. All of these places seem too harsh for survival. Still, life endures. Scientists use the term psychrophiles for creatures that thrive in the cold. The word means cold-loving, and it describes a wide range of organisms, from tiny microbes to fish, insects, and even certain plants. These beings live where temperatures never rise above freezing, and where energy is scarce. Imagine the deep Antarctic ice, where the sun barely rises during winter. Beneath the surface, trapped inside the frozen layers, tiny microbial cells can remain alive for thousands of years. Their chemistry slows almost to a halt. Yet, like a candle flame protected by glass, a spark of life remains, waiting. Or picture the Arctic Ocean covered by sheets of ice. Beneath the surface, plankton drift in the frigid water, providing food for fish, whales, and seals. Even here, where every drop of water feels like a knife against human skin, a web of life continues quietly. This is a paradox of cold. What appears lifeless can be teeming with hidden survival strategies. The cold does not silence life completely. It teaches it patience, stillness, and resilience. How does life endure such piercing cold? The answer lies in adaptation. Many cold-dwelling organisms use what scientists call antifreeze proteins. These remarkable molecules prevent ice crystals from forming inside their cells. Normally, when water freezes, sharp crystals grow and tear through the delicate structures of life. But antifreeze proteins gently attach to these forming crystals, halting their growth, keeping cells intact, even at temperatures well below zero. Some fish in Antarctica, for example, the Antarctic ice fish, owe their survival entirely to these proteins. Their blood contains natural antifreeze, circulating quietly, preventing their bodies from freezing solid. It is as if their veins carry not just life, but a subtle, invisible shield against the cold. Microbes in glaciers survive differently. They slow their metabolism to nearly nothing, consuming tiny amount of stored energy. In this state, they can persist for thousands, perhaps even millions of years. Like dreamers locked in deep sleep, they wait until warmth or liquid water returns. Insects, too, have clever strategies. Certain beetles and moths in the Arctic produce sugars and alcohols in their bodies. These act like antifreeze, lowering the freezing point of their bodily fluids. Even when the air temperature falls far below zero, they remain alive, ready to awaken when spring arrives, and beyond survival in the moment. Many organisms prepare for the cycles of cold and warmth. Seeds of tundra plants may remain buried, frozen for decades, until the rare summer thaw allows them to sprout. Life is patient in the cold. It knows how to wait. The story of cold-loving life is not only about endurance. It is also about the hidden beauty of adaptation. Scientists study psychrophiles not only to admire their resilience, but to learn from their strategies. Enzymes from cold-dwelling microbes, for instance, can work efficiently at very low temperatures. These enzymes are used in industries on Earth, in food processing, in laundry detergents, in biotechnology, allowing work to be done without added heat. The frozen world, in this way, contributes silently to human life far from the poles. And the lessons go further. The existence of life in freezing conditions changes the way we think about other worlds. Mars, for example, is a frozen desert. Europa and Enceladus, moons of Jupiter and Saturn, hold icy shells over hidden oceans. If life can persist in Earth's glaciers, in frozen lakes beneath kilometers of ice, then perhaps similar life may lie quietly beneath alien ice, waiting for us to discover it. There is also a more personal lesson. Cold teaches slowness. Life in these places moves gently, conserving energy, conserving motion. It reminds us that survival is not always about speed or strength. Sometimes survival is about patience, about waiting with quiet endurance until the world shifts in your favor. And so, in the stillness of freezing places, we discover that life is never truly absent. It whispers through the frost, it glimmers beneath the ice, and though hidden from our hurried eyes, it continues, gently, persistently, against the silence of cold. The ocean covers more than 2/3 of our planet. Its surface shimmers in sunlight. Its waves whisper against the shore. But beneath that familiar blue lies a world so vast, so deep, and so hidden that we have explored only a tiny fraction of it. As we descend, light begins to fade. Colors drain away, first reds, then oranges, then yellows. Soon, only deep blues remain, until finally, even blue disappears. At just a few hundred meters down, the ocean becomes a place of near total darkness. The deeper we go, the greater the pressure becomes. Every 10 meters adds another atmosphere of weight. At the bottom of the Mariana Trench, the deepest place known on Earth, the pressure is more than 1,000 times what we feel at the surface. For human, or even for most machines, this crushing force would mean instant destruction. But life finds a way. This hidden world is home to creatures we are only beginning to know. Some live in the mid-water zones, drifting in the twilight. Others cling to the seafloor, scavenging and hunting in complete blackness. And still others gather around hydrothermal vents, where scalding water erupts from the earth. It is easy to think of the deep ocean as empty, but in truth, it is filled with quiet resilience. Strange fish with glowing organs, jelly-like beings that pulse gently in the dark, microbes that feed on chemicals rather than sunlight. Each has been shaped by the immense pressures and endless night. This is a realm of survival without light, without warmth, without certainty, a realm where life is adapted, not to abundance, but to scarcity. And yet, somehow, this scarcity has created forms of beauty that seem dreamlike, even otherworldly. How do creatures survive in such a forbidding world? The answers are as varied as the beings themselves. Some rely on bioluminescence, the ability to create light within their own bodies. Tiny chemical reactions inside their cells produce soft glows, flashes, or twinkling signals. For some, this light is a lure, like the dangling bulb of the anglerfish, drawing prey closer in the dark. For others, it is a form of communication, flashes exchanged between mates or warnings sent to rivals. And for many, it is camouflage, a gentle glow on the belly that matches the faint light from above, hiding them from predators below. Others adapt with incredible sensitivity. Their eyes grow enormous, tuned to capture the faintest hints of light. Or, if sight is no longer useful, they abandon eyes altogether, relying on touch, vibration, or chemical senses to find food. At such depths, food is scarce. Most of it drifts down from above in a constant rain of tiny particles called marine snow. This snow is made of dead plankton, bits of organic matter, and small fragments from the surface world. Creatures of the deep often drift slowly, conserving energy, waiting patiently for the snow to fall. They live at a pace that matches their environment, slow, deliberate, careful. At the very bottom, scavengers like giant isopods roam, feasting when opportunity arrives, and fasting for months in between. In this way, they echo the patience of cold world creatures, teaching us again that survival is not always about abundance, but about endurance. And then there are the vent communities, clusters of life built around hydrothermal vents. Here, microbes draw energy not from sunlight, but from the chemicals rising from Earth's crust. They form the base of a food web that supports tube worms, crabs, shrimp, and fish. It is a reminder that life is not bound to surface, but can spring up even in the hidden furnaces of the deep. The deep ocean is more than a place. It is a mirror of possibility. It shows us that life does not require sunlight, that warmth and air are not absolute requirements, that survival can be built upon patience, scarcity, and stillness. For scientists, this has vast meaning. If life can endure crushing pressures, endless night, and isolation here on Earth, then perhaps it can exist in similar oceans beneath the icy crusts of other worlds. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both are believed to have hidden oceans, and within those oceans, warmed by energy from below, could be life forms as strange and beautiful as those we have discovered here. Even for us, in our daily lives, there is a lesson in the deep ocean that survival often comes not from fighting the world, but from bending with it, from conserving energy, from moving slowly, patiently, from glowing softly in the dark instead of burning brightly in the sun. The deep ocean whispers that there is strength in stillness, that beauty can exist even in the unseen, and that life, no matter how hidden, will always find a way. High in the mountains, the air grows thin. Each step feels heavier. Each breath feels shorter. For us, the lack of oxygen makes climbing exhausting. Our bodies gasp, our hearts race, and sometimes we grow dizzy with altitude sickness. Yet, the peaks of our world are not empty. They are home to plants, animals, and even entire human cultures, all of which have found ways to endure in this thin and fragile air. The challenges of high-altitude life are many: low oxygen, freezing temperatures, intense winds, stronger radiation from the sun, and soil that is often poor in nutrients. To survive here requires more than just endurance. It requires transformation. Some animals have developed larger lungs or more red blood cells to capture and carry precious oxygen. Some plants stay low to the ground, hugging the soil to avoid the fierce winds. And many creatures live at a slower pace, conserving energy in a world where every breath is precious. The Andes, the Himalayas, the Tibetan Plateau, the Rocky Mountains, the Ethiopian highlands, across the world, these towering landscapes show us countless examples of adaptation. And in their quiet strength, we see the persistence of life in the face of what seems impossible. For us, these heights are breathtaking in more ways than one. They are beautiful, awe-inspiring, yet also humbling. They remind us that life's reach does not stop at the tree-line, but continues, climbing ever upward into the thin air of the sky. Let us look closely at some of the beings who call these high places home. Consider the yak, a gentle giant of the Himalayas. Its thick fur shields it from bitter winds. Its heart and lungs are larger than those of lowland cattle. Its blood carries oxygen more efficiently, and it grazes calmly on the sparse grasses of the high plateau. For the people of Tibet, the yak is not just an animal, but a companion, a source of milk, wool, and strength. It is a symbol of survival, embodying the ability to thrive where others could not. Now imagine the bar-headed goose. Every year, it makes one of the most astonishing migrations in the animal kingdom. It flies over the Himalayas, soaring above Mount Everest itself, at altitudes where the oxygen is only a third of what it is at sea level. Its blood binds oxygen tightly. Its wings beat steadily, and its body conserves energy with perfect efficiency. No other bird flies higher with such determination, a reminder that even the sky's thin veil is not a barrier to life. There are also the mountain flowers, small, delicate, yet impossibly resilient. They bloom for only a short time each year, when snow melts briefly and the soil softens. Their colors brighten the harsh slopes, attracting the few insects that also make their home at such altitudes. They live quickly, taking advantage of the rare warmth before winter sweeps in again. And we cannot forget the people. In the Andes, the Quechua and Aymara communities. In Tibet, the Sherpa and other Himalayan groups. In Ethiopia, the Amhara and Oromo who live on the high plateau. All have adapted over generations, with bodies tuned to the thin air, and cultures that draw strength from the mountains. For them, altitude is not an enemy, but simply home. These stories, each one, show us that high places are not barren wastelands. They are vibrant ecosystems, filled with beings who have bent themselves gently to the shape of their environment. The mountains hold lessons, not only for science, but also for the spirit. Scientifically, the adaptations of high-altitude life help us understand resilience. How do lungs expand their capacity? How does blood change its chemistry? How do plants manage photosynthesis with so little air? These questions guide medicine, physiology, and even our plans for exploring space. For astronauts who will one day live in low-oxygen environments on other worlds, the answers may be essential, but there is also a softer lesson. High-altitude life reminds us of patience, of the quiet strength that comes from adapting rather than resisting. A yak does not fight the cold, it accepts it, wrapping itself in warmth. A mountain flower does not demand endless days of summer. It blooms in the briefest window and then rests. And a goose does not avoid the heights. It passes through them gracefully, trusting in its body's quiet power. When we look at these creatures and at the people who live among them, we see a reflection of endurance, that even when the air is thin, life finds ways to breathe deeply. Even when the climb is steep, life continues upward. Even when the world grows harsh, life responds with gentleness, with adaptation, with calm persistence. And so, in the high altitudes of our planet, we find not emptiness, but resilience, a quiet affirmation that wherever Earth offers challenge, life responds not with despair, but with creativity. The desert stretches wide and quiet, an ocean of sand, of stone, of stillness. By day, the sun blazes, pouring heat onto the land without mercy. By night, the temperature drops suddenly, leaving the earth cold and bare. To us, deserts may seem empty, lifeless, places where little can survive. But in truth, they are full of hidden life, subtle, careful, and remarkably resilient. The greatest challenge of the desert is not just heat, but dryness. Water, the essence of life, is scarce. Rains come rarely, sometimes years apart. And when they do, they vanish quickly, sinking into the thirsty soil. To survive here is to master the art of conservation. Every drop matters. Every choice counts. And life in the desert moves in rhythm with the rarest of gifts, water. Some animals rest by day, avoiding the burning heat, and emerge only at night. Some plants spread roots deep below, reaching for hidden reservoirs. Others store moisture in leaves, stems, or even spines. In the desert, nothing is wasted, and every adaptation tells a story of patience. The Sahara, the Arabian Desert, the Mojave, the Gobi, the Kalahari, each desert carries its own personality, yet all share the same truth. They demand respect, and they reveal the quiet genius of survival. Imagine the camel, often called the ship of the desert. Its long legs keep its body above the scorching ground. Its hump stores fat, not water, a reserve of energy that sustains it during long journeys. Its nostrils can close against blowing sand, and its body loses water so slowly that it can travel for days without drinking. For centuries, camels have carried travelers across endless dunes, partners in endurance, and symbols of patience. Then there's the kangaroo rat of North America's deserts. Small, delicate, but astonishingly efficient. It can live an entire life without ever drinking liquid water. Instead, it draws moisture from the seeds it eats. Its kidneys are so efficient, they produce almost no liquid waste. A tiny creature, surviving in a land that seems impossible for life. Consider also the cactus, standing silently under the sun. Its thick, fleshy body stores water. Its spines, sharp yet beautiful, guard against thirsty animals. And its shallow roots spread wide, ready to drink the brief rains the moment they fall. Some cacti can hold enough water to last for years. Silent reservoirs, waiting patiently for the desert's next gift. Even insects show us marvels of adaptation. In the Namib Desert, the fog-basking beetle climbs to the tops of sand dunes at dawn. It raises its body to the breeze, collecting tiny droplets of fog on its back. Those droplets roll down into its mouth, offering a drink in a land where rain almost never falls. And the desert is not silent. At night, when the air cools, the land stirs with life. Owls glide between rocks. Foxes with large ears listen for the faintest sounds. Lizards dart softly over the sand. The desert sleeps by day, but awakens by night, revealing its hidden richness to those who wait patiently. The desert, though harsh, is a teacher. It whispers to us about simplicity, about balance, about patience. Life here does not waste. Every movement is purposeful, every adaptation finely tuned. The kangaroo rat does not seek rivers, it lives with seeds. The beetle does not wait for storms, it gathers fog. The cactus does not chase abundance, it holds on to scarcity and thrives with little. In many ways, the desert mirrors challenges we face in our own lives. When resources are limited, how do we endure? When conditions are harsh, how we find peace? The desert answers quietly, by conserving, by adapting, by moving gently with the rhythm of the land. Science, too, looks to deserts for inspiration. Engineers study the fog-basking beetle to design materials that harvest water from the air. Architects look to desert plants to create buildings that stay cool under the sun. And survival experts learn from animals like the camel, discovering ways to conserve water in emergencies. But beyond science, the desert offers a kind of spiritual calm. Its vast emptiness can feel overwhelming, yet within that emptiness lies peace. The horizon stretches endlessly, reminding us of patience. The shifting dunes tell us that nothing is fixed, even in silence. And the stars, shining brightly over the dark desert sky, remind us that even in the emptiest places, beauty is abundant. The desert, then, is not lifeless, but full of wisdom. It shows us that survival is not about abundance, but about balance. That thriving is not always about speed, but about endurance. And that beauty, even in the harshest places, can be found if we learn to see with patience. When we think of water, we imagine it as a gentle, universal giver of life. Clear rivers, quiet lakes, soft rain falling from the clouds. But not all waters are gentle. Some waters are harsh, burning with acid, or laced with alkali. To us, such waters might seem deadly, corrosive, unfit for drinking or bathing. And yet, to certain organisms, these places are home. Acidic waters often form near volcanic regions, or in mines where sulfur mixes with rain. They may bubble with heat, tinted yellow or red from dissolved minerals. Their pH is low, meaning they are sharp, biting, even able to dissolve metal. Imagine lakes where fish cannot swim, where the air smells of sulfur, where every drop seems hostile to life. Alkaline waters are the opposite. Their pH is high, not sour but bitter. They form in closed lakes where evaporation leaves behind salts and carbonates. These waters may appear still and silent, yet they are filled with strange chemistry that challenges survival. To us, both acidic and alkaline worlds are hostile, but life, as always, finds a way. Tiny microbes, called extremophiles, thrive here. They have evolved to protect their fragile proteins from dissolving, to keep their inner chemistry balanced against a harsh outside world. And in their quiet survival, they remind us that even the strangest environments can be made into a home. Let us wander into the steaming pools of Yellowstone National Park. Here, brightly colored mats of bacteria cling to rocks and hot springs. Some of these waters are acidic, bubbling with sulfur, yet microbes such as acidithiobacillus live here, feeding on iron and sulfur compounds. Their presence paints the springs in vibrant shades of orange, yellow, and red. What seems poisonous to us is simply nourishment to them. Travel now to Lake Natron in Tanzania, a shimmering alkaline lake. Its water so caustic they can burn skin. Its surface glows with reds and pinks, colored by salt-loving microbes. And yet, flamingos gather here by the thousands, nesting on islands that form in the shallow waters. They feed on the very algae that thrive in the salty environment. For them, What is toxic to others becomes a sanctuary, a place where predators cannot follow. Consider also the mines of Spain, where the Rio Tinto flows like a river of blood. Its waters are acidic, rich with iron. Scientists study this river closely, for it resembles conditions on Mars. And still within its depths, life persists. Microbes endure in the red flow, whispering to us that even other planets may harbor unseen resilience. Even in caves, droplets of acidic water trickle over rocks, yet microbial films shimmer on their surfaces. These hidden colonies remind us that adaptation is not limited to the grand, visible world, but takes place quietly, molecule by molecule, unseen and enduring. What do acidic and alkaline worlds teach us? They show us that life is not fragile in the way we might think. It does not require perfect conditions, gentle climates, or soft waters. It can endure in places that defy our imagination. For science, these organisms are keys to understanding resilience. They're enzymes and membranes, able to function in extremes, inspire biochemistry and medicine. Some may help us design new ways of processing waste, or extracting minerals, or even treating disease. Others give clues about how life might survive on distant planets, beneath strange skies and in alien seas. But there is also a gentler lesson here. When we see these creatures surviving in harsh waters, we are reminded of adaptability, that even when the environment seems hostile, it is possible to adjust, to bend, to continue. The microbes in acidic pools do not resist the acid. They reshape themselves around it. The flamingos of Lake Natron do not flee from the alkaline waters. They make the place their refuge. In their endurance, we see a reflection of our own lives. For we too face challenges that sometimes feel corrosive, overwhelming, too sharp to endure. Yet, like these desert lakes and sulfur springs, there is often a hidden balance, a way to turn hardship into strength. And so, as we look upon these acidic and alkaline worlds, we are not seeing lifeless wastelands. We are seeing laboratories of resilience, sanctuaries of adaptation, quiet proofs that life is stronger, more flexible, and more creative than we often believe. Radiation, it is everywhere, though unseen, streaming from the sun, drifting through space, seeping from rocks deep beneath our feet. For us, radiation can be dangerous, damaging the very molecules of our bodies. It can harm DNA, break cells, and cause sickness over time. We wear protective clothing in hospitals where radiation is used. We shield spacecraft and nuclear plants against its effects. For humans, survival in strong radiation seems impossible without heavy defenses. And yet, life has found a way. There are organisms, small and simple, that have evolved extraordinary resistance to radiation. They endure what would kill us in moments. They survive doses thousands of times higher than what a human could withstand. To understand them is to glimpse the deepest resilience of life itself. How can a fragile cell, so small, endure such invisible violence? The answer lies in patience, repair, and ingenious strategies of survival. Among the most famous of these survivors is Deinococcus radiodurans, a tiny bacterium, yet sometimes called Conan the bacterium, for its nearly indestructible nature. It can survive intense blasts of radiation, freezing, dehydration, even the vacuum of space. How does it manage this? Its secret lies in its DNA. When radiation shatters its genetic code into fragments, this microbe calmly begins to repair itself. Piece by piece, strand by strand, it rebuilds its genome, restoring order from chaos. In hours, what seemed destroyed is whole again. Scientists marvel at its ability, and study it closely, hoping to learn how cells might better resist damage, even in humans. But this bacterium is not alone. In the ruins at Chernobyl, where radiation lingers in abandoned forests and empty towns, life has returned. Pine trees grow, animals wander freely, and microbes thrive in the very soil. Some fungi have even been found to use radiation as energy. They contain dark pigments called melanin, the same pigment that colors our skin. And somehow, this pigment seems to help them harvest the energy of radiation, much like plants harvest sunlight. A strange, quiet transformation of something destructive into something sustaining. Even tardigrades, the tiny water bears known for their resilience, can endure radiation. When threatened, they curl into a dormant state called a ton. In this form, their bodies produce protective proteins that shield DNA from harm, and so they drift unharmed through radiation that would devastate most other creatures. Each of these beings, bacteria, fungi, tardigrades, reminds us that radiation, though dangerous, is not always the end. With the right adaptations, even the invisible storms of energy can be endured. What can radiation-resistant life teach us? For science, the lessons are profound. If bacteria can rebuild DNA after it is shattered, can we learn to repair our own cells more effectively? If fungi can harvest energy from radiation, could we design new systems of energy capture useful for space travel or medicine? If tardigrades can shield their fragile bodies, could their proteins help protect astronauts venturing beyond Earth? These possibilities inspire researchers, and already fragments of knowledge from these organisms are shaping medicine, genetics, and space exploration. But beyond science, there is a gentler wisdom here. Radiation is a force we cannot see. It is silent, invisible, often feared, and yet life has shown that even this hidden storm can be faced with resilience. Deinococcus does not panic when its DNA is broken. It rebuilds calmly, patiently, without hurry. The fungi at Chernobyl do not flee from radiation. They adapt, transforming it into something useful. The tardigrade does not resist endlessly. It rests, conserving itself until the danger has passed from them. We learn that even in the face of forces we cannot control, there are ways to endure, sometimes through repair, sometimes through transformation, sometimes through rest and patience. And so, radiation resistance is not only a biological marvel, it is also a quiet metaphor that even in the harshest, most invisible trials, survival is possible. Life will bend, adapt, and continue. It always finds a way. Space silent, endless, dark, a place without air, without warmth, without shelter. For most life, space is impossible. Without pressure, water boils away. Without oxygen, breathing ceases. Without protection, radiation cuts deep into fragile cells. And yet, here on Earth, there are places that echo the conditions of space. High mountain peaks where the air is thin and radiation is strong. Dry valleys in Antarctica where almost no liquid water remains. Salt flats, deserts, volcanic craters, and even the vacuum-like environments deep underground. In these space-like places, life has learned to endure, and by studying it, we glimpse how survival might be possible beyond our planet. For astronauts, and for the dream of exploring other worlds, this is more than curiosity. It is preparation. Every microbe, every tiny survivor becomes a teacher, showing us the possibilities of life among the stars. Among the most extraordinary survivors are the tardigrades, tiny, water-loving creatures no bigger than a grain of sand. And yet, they are among the toughest beings we know. When conditions grow extreme, tardigrades enter a state called cryptobiosis. They curl into a tiny ball, a ton, shutting down almost all activity. In this form, they can survive the vacuum of space. They can endure radiation, freezing, even boiling. They have even been sent into orbit, exposed directly to the cold and radiation beyond Earth. And still, when brought back, some of them revived, continuing their slow, gentle lives as though nothing had happened. Microbes, too, astonish us. Spores of bacteria have been shown to survive years in space. Protected by their tough coats, they drift silently, waiting for better conditions. In labs, scientists expose spores to vacuum and radiation. And yet, some remain alive, whispering the possibility that life might travel between planets on rocks or dust, a theory called panspermia. Even simple lichens, combinations of fungi and algae, have been tested in space, placed on the outside of spacecraft, exposed directly to the harshness of orbit, and when returned, many of them still lived, calmly photosynthesizing once more, as if the cold silence of space was only a passing dream. These creatures remind us that survival does not always mean comfort. Sometimes it means waiting. Sometimes it means slowing down until the danger has passed. And sometimes it means being strong enough to endure the unimaginable. Why do these stories matter? Because they reshape what we believe about life. If microbes, tardigrades, and lichens can survive space-like conditions, then perhaps life elsewhere in the universe is not so rare. Perhaps Mars, or the icy moons of Jupiter and Saturn, or even distant exoplanets, may hold hidden resilience. Perhaps life can move between worlds, carried silently by rocks ejected from impacts, crossing light years of space before finding a new home. For humans, these lessons are practical too. We dream of settling on Mars, of building stations on the moon, of sending ships beyond Earth. To do this, we must learn endurance. We must protect our bodies against radiation, find water in barren lands, and adapt to thin atmospheres. By studying Earth's space like survivors, we are slowly gathering the knowledge we need. But beyond the science, there is also a gentler truth. These creatures remind us that life is persistent, not because it resists change, but because it bends with it. The tardigrade does not fight the vacuum. It rests, waiting patiently until warmth and water return. The spore does not demand perfect conditions. It drifts silent until the right moment arrives. The lichen does not fear the stars. It simply endures, holding on to its quiet bond between fungus and algae. And so, in them, we see a reflection of resilience for ourselves. That even when we face emptiness, silence, or conditions that feel too harsh, survival is possible. Perhaps not through resistance, but through patience, through adaptation, through quiet endurance. As we look to the future, to journeys beyond Earth, we carry with us the wisdom of these tiny teachers. That life, in its infinite creativity, finds ways to endure even in the cold, silent, airless void, and that we, too, may one day thrive in places we once thought impossible. All through our journey, we have seen life in its most astonishing forms. Not the obvious kind of life, not tall trees or green fields or the gentle creatures we meet every day, but life at its edge, life surviving where it should not. Why does this matter? Because it shows us the hidden strength of existence, that the spark of life is not fragile in the way we often imagine. It is not limited to warm valleys, calm waters, or comfortable climates. Instead, It stretches outward, reaching into extremes: heat, cold, pressure, dryness, radiation, even space itself. When we study life in extreme places, we are reminded that survival is not about ease. It is about creativity. The camel in the desert stores energy differently. The yak at high altitudes carries oxygen more efficiently. The microbe in an acidic pool repairs its DNA in ways we could never imagine. Each one reveals a different path, a different answer to the question of endurance. This matters because it expands our understanding of what is possible. It tells us that even when conditions seem unbearable, there is often a way forward. It whispers to us, in the gentlest voice, that limits are not walls, but invitations to adapt. And in this truth, there is something deeply comforting. Because if life can endure in boiling springs or frozen seas, perhaps we, too, can endure the challenges of our own lives. Perhaps resilience is not about strength alone, but about flexibility, patience, and the quiet courage to keep going. The scientific importance of extreme life is immense. Every discovery about these organisms deepens our knowledge, and sometimes reshapes our future. When scientists study microbes that survive radiation, they imagine new ways to repair human DNA, to fight disease, to protect astronauts. When engineers learn from beetles that drink from fog, they design materials that can gather water in deserts. When researchers look at tardigrades, they see models for surviving long space journeys. And when we find microbes in acidic rivers or alkaline lakes, we glimpse possibilities for mining, waste treatment, and even medicine. But the importance is not only scientific. It is also human. These stories inspire us. They give us perspective. We look at a small beetle, standing still on a dune, drinking from fog. We look at a flamingo, turning a harsh lake into a sanctuary. We look at microbes, quietly thriving where nothing else can. And suddenly, we realize life is not defined by comfort, but by creativity. For humanity, this matters because our future will take us into extremes, too. As we explore other planets, as we face changing climates on Earth, as we build technologies and dream of new worlds, we will carry the lessons of these survivors with us. They will be our teachers, our quiet guides, reminding us that adaptation is always possible. And on a softer level, these stories matter because they humble us. They remind us that survival is not our gift alone, that tiny creatures, invisible to our eyes, have already mastered challenges we still struggle to imagine, and that life in its vast variety is stronger and more resourceful than we ever dreamed. Beyond science, beyond technology, there's a deeper reason why all of this matters, because it reminds us of wonder, that the world is far more mysterious, far more astonishing than it first appears, that even in silence, even in emptiness, there's life, quietly enduring, quietly adapting, quietly thriving. When we see this, we feel connected to the microbes beneath the sea, to the flowers on mountain slopes, to the beetles in deserts, and to the birds flying over the highest peaks. They are different from us, yet they carry the same spark, the same persistence, the same quiet determination to continue. And so, when we feel small or fragile or uncertain in our own lives, these stories give us comfort. They tell us that survival is not about being unbreakable. It is about being able to bend, to rest, to wait, to adapt. It is about finding strength in unlikely places and beauty in unexpected forms. This matters because it changes how we see ourselves, not as separate from the extremes of the earth, but as part of the same grand pattern of resilience. And it changes how we see life beyond Earth, to perhaps the universe is not empty after all. Perhaps, scattered among the stars, there are other sparks, waiting, adapting, thriving in places we cannot yet imagine. And so, this journey into extreme survival is not just about science. It is about hope. It is about wonder. And it is about the quiet realization that life, in all its forms, is far stronger, far more creative, and far more enduring than we ever thought. And now, we come to the end of our journey. We have wandered through deserts and oceans, mountains and caves, heat, cold, silence, and space itself. And everywhere we have found life soft, quiet, persistent life, reminding us that survival is always possible. As you rest now, may these stories stay with you. May they bring you comfort, knowing that resilience is not loud or forceful. It is quiet, gentle, patient. And may they remind you, as you drift into dreams, that you too carry the same resilience within you. Thank you for joining me tonight. May your sleep be deep and peaceful. May your dreams be gentle and full of wonder. Good night and goodbye, softly, calmly, until we meet again.